integers sorting via network coding. Let us see what is lower bounds for external memory integers sorting via network coding in further slides briefly. So let us see the abstract for this. Sorting extremely large data sets is a frequently occurring task in practice. These datasets are usually much larger than the computer's main memory. Thus, external memory sorting algorithms first introduced by Agarwal and Mitter, and they are invented this in 1988 and are often used. The complexity of comparison-based external memory sorting has been understood for decades by now. However, the situation remains elusive if we assume the keys to be sorted are integers. In internal memory, one can sort any set of n integer keys of big of log n bits each in big of n time using the classic radix sort algorithm. However, in external memory, there are no faster integer sorting algorithms known than the simple comparison based ones. Whether such algorithms exist has remained a central open problem in external memory algorithms for more than 3 decades. Let us see the introduction. Sorting is one of the most basic algorithmic primitives and has attracted lots of attention from the beginning of the computing era. Such many classical algorithms have been designed for these problems such as merge sort, bubble sort, insertion sort, etc. As sorting extremely large data has become essential for many applications, there has been a strong focus on designing more efficient algorithms. For sorting big data sets, these datasets are often much larger than the computer's main memory, and the performance bottleneck changes from the being the number of CPU instructions executed to being the number of access to slow secondary storage. In this external memory setting, one usually uses the external memory model to analyze the performance of algorithms. External memory algorithms are designed to minimize the number of input and output between the internal memory and the external memory. Example, hard drives, cloud storage, etc. And we measure the complexity of an algorithm in terms of the number of inputs and outputs it performs. So let us see about network coding. The field of a network coding studies the following communication problem over a network. Given a graph G with the capacity constraints on the edges and k data streams, uh, each with a designated source sink pair of nodes in G, what is the maximum rate at which data can be transited concurrently between the source sink pairs? A simple solution is forwarded to the data as indivisible packages. Lower bounds for matrix transpose. We also reprove an analog of the lower bounds by Adder et al. For the matrix transpose problem. This time, without any assumptions of obliviousness, in the matrix transpose problem, the input is an n by n matrix A with omega bit integer entries. The matrix is given in the row major order, meaning that each row of A is sorted in n by v blocks and B consecutive entries each. The goal is compute a transpose that is output the column major representation of A which stores n by b disk blocks. Let us see about preliminaries. We know we now give a formal definition of the k-pace communication problem and the multi-commutative flow problem. A k-pace communication problem. To keep the definition as simple as possible, we restrict ourselves to direct acyclic communication networks graphs, and we assume that the demand between every source sink pair is the same. This will be sufficient for our proofs. For a more general definition, we refer to the reader. The input to the K-based communication problem is a directed acyclic graph G equal to V comma E, where each edge belongs to edge E and has a capacity of C of E belongs to R. There are K sources S1 to Sk and they are belong to V, and K sinks T1 to Tk that belongs to V. Typically, there are also demand Di between each source sink pair, but for simplicity, we assume Di equal to 1 for all pairs. This is again sufficient for our purpose. Proof overview. In this section, we give an overview of the main ideas in our proof and explain the barriers we overcome in order to remove the assumption of obliviousness. To prove our lower bound for external memory sorting, we focus on the easier problem of permitting in the permutation problem. We are given an array A of n entries. The ith entry of A stores a omega bit data item di, and A destination pi I is produced to output array C, where di is sorted in entry C of pi of I. The arrays A and C are both sorted in disk blocks such that each disk block of A stores log of n plus omega by b entries, and each disk block of C stores omega by b entries. The maximum number of entries that can be packed in a block. A sorting algorithm can sort a log of n plus omega bit integer keys can be used to solve the permutation problem by replacing each entry pi of I, comma d of I with the integer pi of I, 2 power omega plus di. In the addition, we think of di as an integer in 2 power omega. Thus, it suffices to prove lower bounds for permitting. External memory lower bounds. As mentioned in the proof in the section 3, we prove our lower bound for external memory sorting via a lower bound for the easier problem of permuting. An input to the permutation problem is specified by a permutation pi of 1, 2 to n, as well as n bit strings di, dn belongs to 0 of 0, I. We assume omega is greater than log of n such that all bit strings may be distinct. The input is given in the form of an array where the ith entry a of I stores the tuple pi of I, di. We assume that the input is given in the following natural way. Each pi of I is encoded as the log of n bit integer, and the di's are given as they are using omega bits for each. Here, this is an image uh, external memory where array two arrays, array A and array C, and there are memory nodes. Memory nodes are connected to these arrays, and this is about this image. Thus, what remains is to argue that E of k is small. That is, we have to show that the Hamming distance between the uniform random x and the nearest y in f is small in expectation. We prove this by considering a concrete distribution over pairs, where z is uniform random in 0, 1, y is uniform random in f, and expected Hamming distance between z and y is small. This is, of course, requires that the joint distribution of z, y is far from a product distribution. If we use t denote the expected Hamming distance between z and y, that it must be the case that E of k is less than or equal to t, since x and z have the same distribution and k gives the distance to the nearest vector in f. We now argue that the t is small for the right joint distribution and is on z and y. Our choice of a joint distribution and our proof is inspired of by the root of IC protocol compression algorithm for non-product distributions given in the seminal work of Barak et al. Pick uniform random numbers k1 and k between 0 and 1. So by doing this we get the y is uniform. Thank you.